So my name is Alex Norton. Today I'm going to be talking about some of the recent and new developments in HPC and AI processor technology, as well as coprocessors and accelerators. To start, let's look at what dominated and has dominated the market for the better part of 2 decades. x86 processors emerged in HPC back around 2002, but by 2006 they contributed to at least 90% of the processors installed in HPC and have maintained that portion of the HPC market until today. Many applications today are written for x86 systems, and x86 based systems have become the standard for most large HPC data centers. There have been many alternatives offered, and some have had minor success in the HPC market, but none yet have supplanted x86 as the HPC processor type of choice. On the right here, you can see a graph that shows the entrance of x86 and how quickly x86 became the market standard for processors. Within the x86 space, Intel has been the dominant vendor for providing x86-based processors. Recently, AMD has brought a product to market that poses a very strong challenge to Intel's market share. The AMD EPYC line has strong performance and price performance benchmarks compared to the Intel x86 line, and has been chosen as the key processor for 2 of the Coral 2 DOE procurements in late 2022 to early 2023. Despite AMD's surge in some of these large deployments of AMD technology, Intel remains the dominant x86 supplier for HPC systems. But as we look towards the future and we look at kind of what has evolved over the past few years and what we expect to occur in the coming years, we do see an influx of both x86 vendor alternatives to Intel, as well as ARM-based processors and other architectures and processor types to address the ever-diversifying workload set of HPC users. And future data centers, we think, are going to be much more heterogeneous by nature, combining many different technology platforms and processor platforms to handle a wide variety of applications, each with specific needs. One of the key areas that people have been, or researchers have been looking at, is the performance per watt, as well as the memory capabilities of various processor technologies and how they stack up against each other. So a question that gets often asked is, where does ARM fit, or where does ARM factor into the HPC ecosystem? As I just mentioned, over 90% of the processors sold are x86 based, but ARM has made a recent surge into the limelight, highlighted by the Fugaku machine at RIKEN. The A64FX chip, which is an ARM-based processor, was developed in conjunction between Fujitsu and RIKEN for an extremely specialized and custom-built processor. This processor, the A64FX processor, really highlights the capability that ARM presents in the flexibility, but also it shows what true co-design between application and processor experts can produce over a long period of time. It is important to note that this processor wasn't developed for many years and cost a lot of money to produce, but the benchmarks and early results that we've seen show that it's a very successful co-design effort. There have also been other major ARM deployments, including the HPE Moonshot program, as well as a few high-profile systems in the UK that are running on ARM chips. But one of the key barriers to adopting the ARM platform is porting codes to ARM. Many of these codes, as I mentioned, are written for x86 systems. So porting them to ARM requires a lot of work, and there has to be a dedicated effort to do so. But for some applications, as RIKEN has shown us, some applications show positive performance gains and strong performance results on an ARM-based platform. This slide shows the up-to-date Hyperion Research ARM forecast. This forecast and these numbers are from the perspective of processor counts deployed in HPC, not spend. As you can see, ARM is rapidly becoming a more important and critical part of the HPC processor ecosystem, fueled, as I mentioned, by the Fugaku machine and other subsequent ARM-based processors. It's important to note that in the major spike in 2021 in this forecast is due to the Fugaku machine itself, which was extremely large and cost over $1 billion at the end to make. On the bottom line, you can see the portion of all HPC processors that are moving towards ARM. In 2019, just over 1% of all processors in HPC shipped were ARM-based, but as we look out towards 2024, that percentage is expected to grow to almost 8% of all processors. So although a small portion, ARM-based systems and ARM processors are growing in adoption at a very high rate right now. Another trend that we're seeing in the processor market are purpose-built processors by end users. As workloads have become much more diverse with the influx of AI and machine learning and deep learning, as well as some of those techniques being applied to traditional modeling and simulation applications, end users have started to design chips that meet their specific needs. Many of these chips are based on ARM technology, which includes the Fujitsu chip we just spoke about. But some other notable purpose-built processors include the 3 processors that AWS has built. Their Graviton 2 processor, which is the basis for many of their high-performance instances, is an ARM-based processor that's only available on their cloud platform. AWS has also made the Trainium and Inferentia chips, which are both machine learning and deep learning oriented processors. Trainium for data center training type of workloads, and Inferentia for inference-based applications. Further, Apple and their M1 chip, which made a huge splash in the more general IT market, shows what true flexibility ARM presents, the ability to have many different cores that address specific workloads or specific actions that can be performed all on the same chip. The Apple M1 is a very interesting and chip to watch, as it not only has high performance for the applications it's designed for, but also what it presents and what it shows the market is capable of. One of the most high-profile accelerators that's been developed by an end user is Google's TPU, which is now in its 3rd version. Google designed their TPU mainly to handle the specific needs of their AI applications. And the TPU, again, is only available on the Google platform, but has shown really strong competition against the GPU and is becoming one of the key technologies to benchmark new processor or accelerator technology against. Beyond those 3, there are other interesting projects going on all around the world. Facebook is making a push and collaborating with multiple chip providers to produce custom chips for their needs. China and Europe are both pushing for indigenous technology for their supercomputers, for their high-performance computing needs, and they are designing and building purpose-built processors internally to handle those applications. These applications branch beyond HPC and technical computing and go into various applications within the AI, machine learning, deep learning space as well. There is some risks though right now in the processor space. The capability to fabricate at smaller nodes has become a international point of concern. As of now, there are only 3 fabs worldwide that can produce processors under 7 nanometers, TSMC, Samsung, and Intel. And so although there is a push towards these lower or smaller process nodes, there is not a large capacity to produce these en masse. And one note, the Apple M1 chip consumes about a quarter or 25% of TSMC's 5 nanometer capacity. So there is going to be a battle and some a push for more diversity and more capability from the fab standpoint to produce these smaller process node processors. Now let's switch gears a little bit and talk about the accelerators and coprocessor technology. The Nvidia GPU, as with Intel's x86-based processors, Nvidia GPUs have become the market standard for accelerators. They originally entered the IT scene as graphics cards for gaming, but it soon became clear that they had strong performance advantages for training applications, AI applications. There has been a strong adoption from the HPC ecosystem in bringing GPUs, deploying GPUs in their large systems, specifically for AI applications. And NVIDIA's one of the strongest parts of NVIDIA's platform is their CUDA platform. The ability for coding and programming, the libraries, all of that being in one cohesive platform has made the GPU family very strong from NVIDIA. But there are drawbacks to GPUs in general. One, GPUs can be very expensive, much more expensive than base CPUs. And you have to be able to justify the utilization for those GPUs, and you have to use them enough to make them cost effective. They're also power hungry. GPUs require much more power to run than a base CPU, and thus their operating cost does go up. And then finally, they are general purpose, but not every HPC application can benefit today from accelerated compute with GPUs. There are a number of applications that are in the process of being modernized by end users to take advantage of GPUs, but for a traditional HPC site that is thinking about deploying GPUs, again, it has to be they have to be utilized enough to make them worth it, because not all applications can take advantage of them today. As with the CPU business, there are current competitors to the Nvidia GPU in the market. AMD's Radeon has been slated as the accelerator of choice for 2 exascale machines in the US. Intel is currently adding a GPU to their portfolio of accelerators, which already includes FPGAs and other more unique accelerators. And Xilinx's FPGAs are also starting to gain more widespread appeal and adoption in HPC, although they might be more challenging to program than GPUs. So NVIDIA GPUs, although the market standard, are starting to see some competition. But as we look at the ecosystem, general accelerators will dominate the market because they need to be able to handle a multitude of workloads. Specific accelerators for single or a couple of applications don't make as much sense to deploy as more general accelerator capabilities. However, there are a number of processors that are emerging in a new market around AI acceleration specifically. These processors, which could be classified as base processors, as accelerators, as coprocessors, there's a wide variety, and they're each targeting specific applications or specific segments of the AI market. Some companies are focused on image or video recognition or natural language processing. Some companies focus on the key technological differences between edge-based processing and data center training. And the market for these is full of energy right now. There's a lot of investment going in. There's a lot of companies that are involved. And it's not just small companies. There are large companies that are also developing some of these more novel and unique processors. One example is Intel, which is developing the Loihi chip, which is a neuromorphic processor, through their Intel Labs, which is a technology that's still a little more on the horizon than GPUs or FPGAs. And I just want to highlight a few recent announcements and deployments of these AI accelerators. San Diego State Computing Center announced the deployment of Habana technology in their Voyager system, which incorporates both Habana's training-based platform and their inference-based platform. Cerberus Systems, which was one of the first companies to make a public announcement of their technology being deployed, deployed another system at Pittsburgh Supercomputing Center. And SambaNova has announced deployments at both Lawrence Livermore and Argonne National Labs. And they also announced recently an impressive Series D round of investment, which made them the most funded AI startup. One of the keys to these smaller AI processor companies is how they get users. And many of them are looking to the cloud to get access to more users. So companies like Grok and GraphCore, Habana, the chips from AWS, the TPU, these are all only available, or for the most part available, on cloud platforms, which is a really great way for them to allow users to try the platform, to get access to it, and ultimately see what works. So in conclusion, there is a growing diversity from the application standpoint. And as more HPC applications become more diverse in their technological needs from a processor standpoint, that will drive a diversity of processors and accelerators. Many of these new applications are under the umbrella of AI, both as standalone AI applications, but also as HPC users apply AI techniques to traditional modeling and simulation applications. Some of the companies in this ecosystem will strive for a more general accelerator capabilities, while others are focused on very specific applications to handle. And as we look towards future HPC deployments and HPC systems, we anticipate them to be heterogeneous in architecture, combining multiple technology platforms to handle a varied workload set. Thank you very much.